Let's suppose that we are given some data on 5 individuals' performance in maths and in economics. Now, from this data, we might be interested in estimating a number of things. So let's start by defining 2 random variables. Let's say that the performance in maths is a random variable which we'll define as x, and performance in economics is a random variable which we'll define as y. Now we know that provided the observations are IID, then the sample mean is an unbiased estimator of the population expectation. So we know that the expectation of the sample mean of math scores is going to be equal to the expectation of X in the population as a whole. So let's start by constructing our estimate. So X bar, remember, is just equal to the sum of all of the observations divided by the number of observations. So it's going to be 60 plus 75 plus 50 plus 30 plus 70 divided by 5, because there are 5 observations, which gives us a sample mean equal to 57. Similarly, we can estimate the variance of X using our S squared estimator. And remember, S squared is an unbiased estimator of the population variance provided the observations are IID. And again, it's 1 over n minus 1 times by the sum from I is equal to 1 to n of the squares of the deviations of the x's away from the sample mean. And we can calculate our estimate of the variance of x is equal to 60 minus 57 squared plus 75 minus 57 squared plus 50 minus 57 squared plus 30 minus 57 squared plus 70 minus 57 squared, all divided by n minus 1. So that would be divided by 4, which gives us an estimate of the population variance of 320. Similarly, we can do the same for economic scores. Now, suppose that we hypothesize that the average score in maths is actually 60%. So let's suppose that our null hypothesis is that the expected score in maths, the average in the population, is 60 against an alternative that the expected value is not equal to 60. How could we test this? Well, in order to test this, first of all, we need to construct a t-statistic. Remember, the t-statistic is just equal to the estimated parameter that we get, so the sample mean, minus the expected value of that sample mean, conditional on the null hypothesis being true, divided through by the estimated standard error of our sample mean. In order to construct our estimate of the standard error of the sample mean, we need to think about what the variance of the sample mean is. And remember, if the observations are IID, then the variance of the sample mean is just equal to the variance of X divided by n. Now, we don't know the variance of X, but we do have an estimate of the variance of X in the S squared. So our estimate of the variance of X bar, let's denote it variance hat of X bar, is just equal to S squared for X divided by the number of observations, which is 5. So that gives us an estimate of the variance of X bar as 320 over 5, which is equal to 64. So our standard error, or estimated standard error of X bar, is just equal to the square root of 64. So our t-statistic is our sample mean, which is 57, minus the expected value of the sample mean if the null had been true. Remember, since the sample mean is an unbiased estimator, this is just the same as the hypothesized value divided through by the square root of the variance of the sample mean, or the standard error of the sample mean, which gives us a t-statistic equal to minus 3 over 8, or minus 0.375. If you look up the critical values in the t-distribution tables, the critical t-value with 4 degrees of freedom is equal to 2.776. And we've got this by looking at the 2.5% measure within the t-distribution. And remember, because we're interested in whether or not it appears in either tail, it's 2.5% in the upper tail and 2.5% in the lower tail. Since our test statistic minus 0.375, since that's a lot smaller in magnitude than 2.776, we fail to reject the null hypothesis. Now we're given some extra information in the next part of the question, in that the scores are taken from different individuals for maths and for economics. And we're going to construct a new variable z, which is equal to the difference of the sample means of maths and economics. So the question is, how will z be distributed? Well, we know a number of things. We know that if the observations are IID, then the expectation of x bar is just equal to the expectation of x. Let's define that as mu x as the expectation of x. We know that the expectation of y bar, again, if the observations of y are IID, then that's going to be equal to the expectation of y, which is mu y. And we know that the variance of x bar is equal to the variance of x over n. Let's denote that as sigma squared x over n, and let's denote the variance of y bar, because the observations are IID, is just equal to sigma squared y over n. Now it's important that these two groups are from different individuals, and effectively the scores in maths are independent from the scores in economics. So let's work out the expectation of z, which is just equal to the expectation of x bar minus y bar, which is equal to the expectation of x bar minus the expectation of y bar. And this is going to be equal to, using our rules that we've got above, mu x minus mu y. Similarly, the variance of z is going to be equal to the variance of x bar minus y bar, which is going to be equal to, since the variance of x bar minus y bar is a bit like saying the variance of x bar plus minus 1 times by y bar, this is equal to the variance of x bar plus minus 1 squared, or plus 1 times by the variance of y bar, minus 2 lots of the covariance between x bar and y bar. Now, this is where it's important that these are different individuals and that we have the individuals are independent from each other. That would mean that the covariance term would be equal to 0. So the variance of x bar is equal to sigma squared x over n, so sigma squared x over n. The variance of y bar is equal to sigma squared y over n. And if the scores in maths and economics were normally distributed, then it would follow that because we're just combining two normally distributed variables, z would also follow a normal distribution with expectation mu x minus mu y and variance sigma squared x over n plus sigma squared y over n. Using the estimates that we've already got, we can get an estimate of z, which is just using our x bar and y bar from before. We can say that our estimate of the expectation of z, let's call it z hat, is equal to the difference of the sample mean, so x bar minus y bar, which is equal to 57 minus 53, which is equal to 4. Similarly, our estimate of the variance of z hat is just equal to the variance of x bar minus y bar, which is going to be equal to the estimated variance of x bar plus the estimated variance of y bar, which is equal to 64 plus 26.5, which is equal to 90.5. It is hypothesized that the expectation of scores in maths, so the expectation of x, is equal to the expectation of y, but that's just equivalent to saying that expectation of x minus the expectation of y is equal to 0, or we could say that the expectation of z is equal to 0. So our null hypothesis can be that the expectation of z, the difference between the scores, is equal to 0, and the HA is that the expectation of z is non-zero. Now, in order to test this, we need to construct a t-statistic, and the t-statistic is just equal to the estimate of z, which is 4, minus the expectation of z if the null hypothesis is true, which is 0, divided through by the estimated standard error of our estimator, which is just equal to 4 minus 0 divided through by the square root of 90.5, which gives us a t-statistic of 0.420. This is much smaller than any reasonable critical value. As a good rule of thumb, we could look at a critical value of 2. Since the t-statistic is very small, we fail to reject the null hypothesis. Up until now, we've assumed that the individuals for maths and for economics are different individuals. Let's now suppose that actually, by mistake, we've discovered that the individual scores, individual 1 is essentially the same person for their maths and economics, similarly for individual 2, individual 3, and so on. And it's hypothesized that the score in maths has a causal impact on the score in economics. So it's decided that you might want to estimate, using OLS, the relationship between the math score x and the economic score y. So an economist has suggested estimating the following relationship. yi is equal to beta 0 plus beta 1 xi plus ui, where yi is the economic score and xi is the math score. Now we know that our OLS estimators for the intercept is just y bar minus beta 1 hat x bar, and beta 1 hat is equal to the sum from I is equal to 1 to n of yi minus y bar, so the d-meaned observations of y, multiplied by the d-meaned observations of x, divided through by the sum of the d-meaned observations of x squared. From the previous question, we know that the sample mean of the math scores, x bar, is equal to 57, and the sample mean of the economics scores, y bar, is equal to 53. So we can construct an xi minus x bar and a yi minus y bar for each of our observations. So for the first observation, we've got a score of 60, so xi minus x bar is 60 minus 57, which is 3. Similarly, 75 minus 57 is 18, and so on. Similarly, yi minus y bar, the average scores in economics is 53, so for the first individual, we've got 50 minus 53, which gives us a difference or a d-mean version of minus 3. For the second individual, the average, the score is 65, the average is 53, so the difference is 12, and so on. To construct the OLS estimates of the slope parameter, we're going to first of all find the product of each of these terms. So 3 times by minus 3 plus 18 times by 12 plus minus 7 times by 2 plus minus 27 times by minus 18 plus 13 times by 7, which gives us that the numerator, the sum from I is equal to 1 to n of yi minus y bar, xi minus x bar, is equal to 770. Similarly, the denominator is equal to the sum of the x minus x bar squared. So that's going to be equal to 3 squared plus 18 squared plus minus 7 squared plus minus 27 squared plus 13 squared, which is equal to 1,280, and that gives us an OLS estimate of 0.602. That suggests that a 1 mark increase in the math score is associated with a 0.602 mark increase in economics. We could also use this in order to get our estimate of the intercept. Remember, beta naught hat is equal to y bar minus beta 1 hat x bar. Y bar is just equal to 53. Beta 1 hat is equal to 0.602. X bar is equal to 57, and that gives us an estimated intercept equal to 18.71. So this suggests that if an individual got 0 in maths, they might be expected to get a mark of 18.7 in economics. Now, it's highly unlikely that what we've got here are causal estimates, because it's likely that there are other things that determine your economics mark other than just your maths mark. It might be the case that if you work hard in maths, that it has a positive impact on your ability in economics, but there are other things such as natural ability or the amount that you work generally, so your ethos, which might impact on both your maths mark and your economics mark. So it's unlikely that what we've got here is a purely causal relationship.